Hello students, this is the 20th part of functions. So this part also based on composite functions concept. So last part I started on composite functions concept. Okay, composite functions, you can composite two or more than two functions. In last class we observed that if f is a function from a to b, g is a function from b to c, there existing new function from a to c, that is called g circle f. Okay, this is called composite function, and you can say composite of f and g circle f and g. Okay, already I explained how to operate g circle f of x. So you can write g of f of x. First f function should have perform, after that g function. So you observe that composite functions won't satisfy commutative property and some problems based on that concept. Today I am going to explain the concept of composite functions, and the composite function is associative. Composite function not commutative, but it is associative. So what is the commutative? F circle g not equal to g circle f actually. Okay, already you know commutative property a star b equal to b circle dot a circle dot of b circle dot c equal to a circle dot b of circle dot c. Any set satisfy this condition, then it is said to be the set is said to be satisfy associative property. So now I want to prove associative property. All of you observe now. Let f maps a to b, comma g map b to c, h maps c to d are three real functions. Okay, are three real functions. Students, now listen. Now by using Venn diagram I want to explain the concept. Students, this is set A, this is set B, this is set D, this is set D. Nana, observe, this is set A, this is B, this is C, this is D. F is function from A to B, G is function from B to C, H is function from A to D. Okay, let X is the element in A, its image is Y, image of Y is Z with respect to Z, Z is image of Z is some K with respect to the function H. Okay, sometime there exists a new function from A to D. What is that? Should identify A to D. F is from A to B and G is from B to C. Already you know that the new function from A to C is nothing but G circle f only, already discussed. Similarly, there is a new function from A to D. We need to identify what is the new function, what is the name of the new function, what is the name of that composite function. Composition of f, g and h. This yellow color one is composition of f, g and h. Nana. So red color one is composition of f and g. G circle f. G circle f is from A to C. Now yellow one is the function from A to D. What is the name of that composite function? Should identify now. Okay. Yeah, observe students, I will write here, okay, next page is better I think. Okay, so f is from A to B, okay, g from B to C. Observe students, observe none here. Interesting thing is, yeah, these two same, no? There is a new function from A to C. What you call that? G circle f. I can say that G circle f is from A to C. Okay, leave it. Now I want to write here students, G circle f is from A to C, Nana, and H is from C to D only, no? What is the meaning of this? There is a new function from A to D. What is the new function? Composition of these two. So that is H circle of G circle f is from A to D. This is new function from A to D. I can call it as H circle of G circle f. I will write now. Here I will write, this is nothing but H circle of G circle f. Okay. So next what happened? First what I did now, A to C composite function I found. After that A to D. Next I will find composite function b to d, then after a to d I will find. First of b to d, then after a to d. So for that I want to use separate diagram. Observe all of you. So this is repeat one result. This is a, this is b, this is c, this is d, a, b, c, d. Nana. This is x, y, z, k, f, g, h. First of all I want to find what is this function, blue color one. After that I will find the red color function. So that is also a to d. Red one is a to d. So blue color one is b to d. First of all I want to find what is that function. I will write here. G is from b to c, nana. H is from c to d. Automatically by the definition there is a new function, that a to d. What is the new function, nana? That is h circle g. H circle g is from b to d. Though what I can write here, h circle g function, this one, h circle g function. Now I want to find a to d new function, the red color one. So I will write now in next page. Students listen. Yeah, what is, nana? F maps a to b. Just we got new function, that is h circle g. H circle g. H circle g is from b to d. So by the definition of composite function, there is a new function from a to d, that is nothing but composition of this with that. So h circle g first, next f, nana. So what I can write, h circle g of or circle of, 1 minute, how to write I will show you. H circle g of circle f, nana, that one. Okay, that is from a to d. Actually here you need to write circle, not there. Okay, 1 minute, I will correct it. Okay, students observe, nana. What happened? 1 minute. What happened? Observe, nana. So here h circle g circle new function from a to d. So this is also from a to d. I will write both. First h circle g. This is not right color. Okay, I want to use another bright color. H circle g circle of f, nana. This is one function. So this is a to d only. What is the previous one? Where is that? Here, h circle of g circle f. Okay, this is also from a to d only. What is the meaning of it? This is one function a to d. This is another function from a to d. These may be equal. These may be equal. When you can say they are equal, their domains are same, their rules are same, then you can say that they are equal. Now you want to check whether the rules are same or not. See, domains and codomains are same, but by observing these two, you can't say that those two are equal functions. Okay, they should start second condition. The rules are same. Already explained the definition of equality of two functions. F and g are two functions defined on the same domain, and f of x equal to g of x for every x belongs to domain, then they are said to be equal functions. Okay. Okay, now interesting thing, nana. Say this is result 2. Say this is result 1. What is our observation is, this function are having same domain and codomain. Okay, the rules are so, if these rules are also same, then I can say that they are equal functions. Okay, what is y, nana? Y is the image of x under f. I will write here. What is y? F of x. What is z? G of y. What is k? H of z. Okay, these are help us to check whether those two equal or not. First of all, I want to take this h circle g circle of f. I will take, nana. Of x I want x. What is image of x under this function I want to find. So according to definition I can write h circle g of f of x I can write. So h circle g of f of x means what, and y. According to definition I can write h of g of y I can write. G of y means z. Z of z means k. So what is the meaning of that? Image of x is k with respect to this new function. Okay, that I will write here. Therefore h circle g circle of f. Actually here you need to write bracket here. Of x equal to k. So this is result number 3. Next I want to take this function, where is this one. Next one I will take that. H circle of G circle f of x what? So what is this? H circle of G circle f of x. To find this, first of all we need to find this. Wait, another color I will to use, that is not right. I want to find this. What is this? Separately. G circle f of x. G of f of x. What is f of x here? Y. G of y? Z. So H of G circle f of x means H of z, that is equal to k. What is the meaning of that? H circle of G circle f of x equal to k. Result number 4. Observe Nana. See 3 and 4. Image of x with respect to this function is k only. Image of x with respect to this function of k means just like the rules are same, the domains and codomains are same, then I can say that they are equal. From 1, 2, 3 and 4 we can say H circle of G circle f is equal to H circle G of circle f. Okay. What is the meaning of that? Composite functions are satisfying associative property. Proof nana this one. That is, composite functions are satisfying associative property. Okay, this is the proof for this. Okay, students? Yeah. Okay, it is not satisfy commutative, but it will satisfy associate. So, important modal problem. In previous example, to find G circle f, G and f are given in rule form, but here they are given in a roster form. But how to find G circle f? I will show you using Venn diagram without using Venn diagram. Okay, students, listen. Okay, what is f given? I will write first of all. What is f and what is z? F is given as 1, 2, 3, 5, 4, 1. Z is given as 1, 3, 2, 3, 5, 1. Okay. So G circle f you want. G circle f. First we need to perform f nana. Next G. Okay. That what is the meaning of that? G circle f domain is what the domain of f. That is the domain of G circle f only. I will write that domain of G circle f is domain of f. Understood? What is the domain of f? Domain of f equal to 1, 3, 4. So indirectly what you want to find on a G circle f of 1 is equal to what? G circle f of 2 equal to what? G circle f of 3 equal to what? Because G circle f of domain also 1, 2, 3 only, no? But the image of 1 with respect to this function, but the image of 2 with respect to this function, but the image of this with respect to this function. Just now we need to find G circle f of 1, G circle f of 2, G circle f of 4, 3, that one. Okay, no problem. Understood, student? That's why G circle f of 1, according to definition, G of f of 1, f of 1, 2, no, f of 1 is 2 only, 2. G of 2, where is this? G of 2 means 3 equal to 3, means image of 1 is 3 with respect to the function G circle f. Next, G circle f of 3 I want, but the definition I can write G of f of 3. F of 3 here 5, f of 3 means 5. G of 5 1. See here G of 1 is 1. The meaning of the 3 is paired with 1 under the new function G circle f. Okay. Next, G circle f of 4 I want, students. So G g of f of 4. F of 4, where is that? F of 4, 1. Here. G of 1, 3. So what happened? 4 paired with 3 under this. Now I will write conclusion here. Students, here I will write G circle F equal to 1 comma 3, 3 comma 1 and 4 comma 3. Okay, this is the G circle F, important model. Okay, students. So next example, F is from R to R, G is from R to R, defined by f of x mod x, g of x mod of 5x minus 2. Then find f circle g of x and g circle f of x. Easy problem. F circle g of x should find. Or to find f of g of x. F of g of x means what? Where is that g of x? Here is modulus of 5x minus 2. So this is in the form f of k, nana. F of k. F of k means mod k. So what happened? Mod 5x minus 2 I can write. So mod means just one mod you can write. That is not a big problem. 5x minus 2. This is the value of f circle g of x. Next, what should find? G circle f of x I want. That is g of f of x. That is g of f of x mod x. So this is in the form g of k. G of k means what? Mod of 5k minus 2. Mod of 5 into mod x minus 2. This is the G circle F. Sometimes we need to open modulus symbol. Here I don't want to open modulus symbol. As it is, I want to take this one as a G circle F of x. Okay. Sometimes we need to open. Actually, while finding this, actually we need to check whether exists or not. Exist, no? If R to R automatically exists, that is not big problem. Okay. Students, important theorems, very important theorems. F map A to B and G map B to C are two 1 functions. Then G circle F from A to C also 1 function. Very important. F is 1 G is 1 and G circle F also 1. Actually here proofs are not required for you people. Okay, but I want to explain. Students, listen. Theorems, this one, proofs I want to write. How I can prove? Observe. G circle F is from A to C 1 means G circle f of x1 equal to G circle f of x2. From this you want to prove that x1 equal to x2. Then I can say that G circle f is 1 function. But the definition already proved, no. F is said to be 1 function from one set to another set. How you proved, nana? Their images are different. We proved their inputs are different. If inputs are different, we want to prove that their outputs are also different. If outputs are same, we prove that inputs are same, like that. This is x1 y1. This is f of x1, f of y1. If these two are different, we prove that these two are different. Okay, means different elements should be paired with the different elements of second. Then only f is said to be 1, like that. If G circle f is, for example, this is G circle f from one set to another set. Actually A to C only, that one. G circle f is said to be 1 means what? Different elements of A should be paired with a different element of C. x1 paired with x1 is paired with what? G circle f of x1 only. x2 paired with what, nana? G circle f of x2 only. If these two are different, this should be different. If these two are same, this should be same. That's what I assumed. G circle f of x1 equal G circle f of x2. If this gives x1 equal x2, then you can conclude that given function is 1. Okay, listen all of you. Let x1 comma x2 belongs to domain bracket A. Which domain? F function domain, this one. Then there exists f of x1 comma f of x2 belongs to B, or you can write codomain. Why? What the reason is? F is a function. Okay, leave it. Next I will write, let f of x1 comma f of x2 belongs to B. Then there exist there is g of f of x comma g of f of x2 belongs to C. What the reason means? G is a function from B to C. Okay. Okay. Now, what is my assumption, Nana? Here, observe here. This is x1, y1, Nana. Yeah, this is f function, g function. It image is g circle f of something, composite function. This image is g circle f of y1. I have assumed these two are same. From that, I will prove these two are same. Then I can say that the resulting composite function is 1, 1. Okay. Let g circle f of x1 equal to g circle f of x2. Understood? Once again, listen to it. This is first set, second set, third set. This is A, this is B, this is C, F, G, Nana. What is the new function? This is g circle f only. No? Here x1 is paired with x1, x2 are two elements in the domain. Its image is f of x1 only. This is f of x2 only. So, what is the image of this under this new function? G of f of x1 only. No? What is the g of f of x2 only? No? Now we want to check whether this function is 1, 1 or not. How? If these two are different, these two should be different. If these two are same, these two should be same. Or these two are same, these two should be same. Okay. So in that way, what is my assumption? G circle f of x1 equal to g circle f of x2. So implies g of f of x1 equal to g of f of x2. So this is in the form of g of L1 equal to g of L2, Nana. Directly I can say L1 equal to L2, no? G of L1 equal to G of L2. Directly I can say L1 equal to L2 because G is 1, 1 function. See, G is 1, 1 function. G is 1, 1 function. G of L1 equal to G of L2. Automatically L1 equal to L2 only, no? Okay. Feel that this is just like L1, this is L2. G of L1 equal to G of L2 implies what, Nana? L1 equal to L2. L1 equal to L2 means f of x1 equal to f of x2. Reason is G is 1, 1. G is 1, 1. Now f of some k1 equal to f of k2. Automatically k1 equal to k2 because what is the reason? F is 1, 1 implies x1 equal to x2 since f is 1, 1. F is 1, 1. So next page I will write what happened, Anna? G circle f of x1 equal to g circle f of x2 leads x1 equal to x2. That is g circle f is a 1, 1 function. Students, important, Nana. Listen, f is 1, 1, g is 1, 1. From A to B, this B to C. G circle f exists new function from A to C. That also 1, 1. Okay. So important thing is, student, this its converse is not true. Its converse is not true. What is the meaning of that? Actually, in previous problem, f is 1, 1, g is 1, 1, g circle f is 1, 1. Now, converse means if this is 1, 1, these two need not be 1, 1. That is its converse. Converse of above theorem is need not be true means here. If g circle f from A to C is 1, 1, then both f and g need not be 1, 1. But f should be 1, 1. Important. But f should be 1, 1. Through an example I explained here, observe, students. A is 1, 2, B is ABC, C is DE, F is given as 1A, 2B, G is given as AD, BE, CE. Here G is not 1, 1. Observe, G is not 1, 1 here. See. A paired with D and C paired with E. Sorry, B is paired with E and C is paired with E. Means G is not 1, 1. Here F is 1, 1 only. But find G circle F. Already explained how to find G circle F. Just now explained, no? How to find G circle F like this. Using that, find G circle F. So for example, your G circle F is 1 comma D, 2 comma E, obviously. So what happened here? This is 1, 1. Observe, 1, 2 to D, 1, 1. So G circle F is 1, 1. But here F is 1, 1. But G is not 1, 1. No? Understood? That's why converse of above theorem is not true means if G circle F from A to C is 1, 1, then F and G need not be 1, 1. But the important thing is F must and 1, 1. G need not be 1, 1 actually. Okay. This is important theorem. Okay, second theorem, Nana. F is onto, G is onto, then G circle F from A to C also onto. Another difficult and important theorem. Nana. First of all, you people know how to prove a function is onto. For example, a function f is from A to B is said to be onto. The range of the function should be equal to its codomain. Or in other words, for example, x is paired with y. So you want to show that every y there is x. Every y there is x. Under the rule y equal f of x. For every y there is x under the rule y equal f of x, then you can say that f is onto. Range equal to codomain. Now observe students. Rough explanation. This is set A, this is set B, this is set C. Nana, A, B, C. F is function from A to B, G is function B to C. So this is G circle F is from A to C. Now you want to prove that this function is onto. If these two onto, you want to prove that this is also onto. These two onto, for example, this is some z element. We want to say for every z there should be x. For every z there should be x in the domain. So that z equal to G circle F of x. Then you can say that a given function is onto. Okay, then by using f and g are onto, then we can prove that G circle F is onto. Listen all of you. For my explanation purpose, I am using a rough sketch here. Here A, here B, here C, x paired with y, y paired with z, f, g. Leave it just. Okay, now listen. Given G map B to C is an onto. What is the meaning of that, Anna? What is the meaning of this? Okay, range of this function equal to its codomain. For every C, there is element in B that should be paired by the rule G. Understood? That I will write. Let some Z belongs to C. Then there exists symbol. Then there exist. Y belongs to B. Compulsory this happens. Y belongs to B, such that Z equal to G of Y. So this is only important step for the theorem, Nana. What I am doing here, observe here, student. This is G function, Nana. This is B to C. For example, Z is there here. What I am saying, for this preimage should be, because this is onto given. No? For every element of C should be images, preimages in domain. Z is there with, it should be their preimage. Let it be Y. That I wrote here. Let some Z belongs to C, for Z is there in C. There exist, compulsory there exist a Y belongs to B, such that Z equal to G of Y, means Z is the image of Y or Y is the preimage of Z. Okay. Okay, students, understood? I hope you people understood how I got the step and how I wrote the step. Next, listen. Next, given F map A to B is 1 1, sir, is onto. Same reason. If F is onto from A to B, means every B there is x. For example, y is there, automatically there should be a new element. There should exist an element which is the preimage of y under this function. Okay. So that I will write now. Okay. For some y belongs to B, there exist x belongs to A, such that y is equal to f of x. Okay, students? Yeah. Now what should prove? That is interesting. Now what should prove? See here, this is what an G circle F, that is function from A to C. G circle is from A to C. See here, for my explanation purpose, this is A, this is C, this is G circle F. Now you want to prove that this is onto, means for every element in C, you want to show that there exists at least one element in A which is the preimage of C, preimage of this element under this rule. Then I can say that function is onto. Okay. So logically I will write now that one. Observe. Now I want to take this. Consider. I want to use another color for that. Wait. Consider Z equal to g of y. So instead of y, what I can write? This I can write. Instead of y, I can write f of x. What I can write? This is g circle f of x I can write. So I will write in next page. Nana. So what I got here? Z equal to g circle f of x. What is the meaning of that? What is the meaning of that? This means for every z belongs to C, there exists x belongs to A, so that what happened? Z equal to g circle f of x. What is the meaning of that? Therefore, g circle f is onto. Very, very important theorem. Nana. Okay, difficult also. Okay. Now here something is given here. Note, this is also important note. Converse of above theorem is not true. Converse of above theorem is not true. What is the above theorem? F and g are onto functions, then g circle f also onto from A to C. So converse means if g circle f is onto from A to C, then f and g need not be onto functions, but g must and onto. G must onto, but g must onto. This is important. Through example I explained here. A is given as a, b given as 1 comma 2 comma 3, c is taken as x comma y, f is defined as a comma 1, b comma 2, g is defined as 1 comma x, 2 comma y and 3 comma y. I found g circle f. I got g circle f is a comma x comma b comma y. Observe Nana, range equal to codomain, means g circle f is onto function. So among these f and g, by using f and g only I found no g circle f. Here g circle is onto, but what happened? What happened here? G is onto only, but f is not onto. Observe 1 comma 2, range is 1 comma 2, but what is the codomain? 1 2 3, means what is the meaning of this? F is not onto, G is onto, G circle is onto, means if G circle is f is onto, so these two need not be onto, but G must and should onto. In this way you can give example. These are called counter examples. To prove that theorem, sometimes you need to disprove theorem, you can use examples. Those are called counter examples. Okay. Next, f from A to B and g from B to C are two bisective functions. Bisective functions. Automatically, g circle f from A to C also bisective. So, easy proof. To prove this, now you need to use theorem 1 and theorem 2 separately. We need to write theorem 1 and theorem 2. So that is nothing but theorem 3. Okay, students? Yeah. Next, some important theorems. People need to remember this. Proofs easy only. Proofs easy only. For some more important theorems, f is bisective from A to B, then f inverse also bisective from B to A. Proof easy only. That's not a big problem. F inverse circle f equal to IA. IA means identity function from A to A. F is from A to B, then f inverse is from B to C only. F inverse circle f is a new function, then that is A to A, that is called IA, I can say. F circle f inverse is IB, that B to B. Okay, you can prove. But another important result, important theorem. So this is important for a descriptive point of view. F A map f is a function from A to B, G is a function B to C, are two bisective functions. These two are bisective functions. Then G circle f whole inverse equal to f inverse circle G inverse. Same thing I proved in relations, but here functions, no. So in functions concept also I want to prove that G circle f whole inverse equal to f inverse circle G inverse. Students, listen. Feel this. This is a function m. Feel that this function is some n. We want to prove that these two functions are equal. How can you prove two functions are equal? One thing, the domain should be same. Second thing, the rule should be same. Indirectly, the domain should be same, their coordinate should be same, their ranges should be same. Meaning of these two. So how can you prove these two functions are equal? First of all, you want to prove that the domains are same. Second part, the rules are same. Then you can say that the two functions are equal with the definition. Okay. So in this way, every time if you want to prove two functions are equal, first of all you want to show that the domains are same. After that, the rules are same. Then you can say that they are equal functions. Okay. Listen all of you. Proof. F map A to B is bisection. Then F inverse from B to A also bisection. Similarly, G map B to C is bisection, then G inverse from C to B is also bisection. Okay, first of all I want to prove that their domains are same. Okay, so I will prove. See here, first of all I want write G circle, G inverse from what? C to D, F inverse B to A, C to D. What is D here? C to B, not D. C to B, this one. Okay. So F inverse B to A. Automatically, with the definition of composite function, there exists new function from A to C. What is that, Nana? F inverse circle G inverse. F inverse circle G inverse is from C to A. This is number 1. So students, what happened, Nana? This is from C to A. I want to put this is also from C to A. First thing. After that, I can say the domains are same. First of all, find G circle F. I want to find G circle F. G circle F. F should write first A to B. G is from B to C. Automatically, G circle F is from A to C. So F is bisective, G is bisective, G circle F is bisective, G circle F is bisective, G circle F whole inverse exists. So what is that? G circle F inverse is from what, Nana? C to A. This is the number 2. Observe 1 and 2. Their domains are same, no? G circle F whole inverse is C to A only. F inverse circle G inverse C to A only. Now you want to prove that their rules are same. Okay. Yeah. Now for that I want to use another separate paper. Just this is A, this is B, this is C, X paired with Y, Y paired with Z. This is F function, this is G function. F is 1 1, G is 1 1, G circle F also 1 1 from A to C. I will write that is also. This is G circle F. Okay, students, what is Y, Nana, here? F of X. Or in other words, I can say that X equal to F inverse of Y. What is Z? Z of Y. In other words, what I can say, Y equal to G inverse of Z also I can write. Okay, what I want something, where is that? Here, you want to show that these two are same, no? First of all, I will take this. F inverse circle G inverse. F inverse circle G inverse. F inverse circle G inverse of Z, what I want to find, equal to F inverse of G inverse of Z by the definition. So F inverse of Z, Z inverse of Z means Y. F inverse of Y means X. What is the meaning of that? F inverse of circle G inverse of Z equal to X. So image of Z is X under this function. Next, what do you want? Image of Z also under this function also X only. Okay. G circle F. Consider G circle F whole inverse of X. We want to prove that Z. This also we want to prove that X. That is important thing. Any method I can use for this. Any method I can use to prove this. Actually, you need to prove this. This is our plan. Okay. Yeah, students. G circle F of X, what, actually? G circle F of X. G circle F of X equal to Z only, no? Here, directly. Okay, what is the meaning of that? What is the meaning of that? What is X here? G circle F inverse of Z I can write now. What is the problem? Okay. So this is 2, this is 3, I can say this is 4, from 1 to 3, 4. From 1, 2, 3 and 4. Okay, what is conclusion here? F circle G whole inverse or G circle F. Okay, G circle F whole inverse. G circle F whole inverse equal to, don't write G inverse circle F, that is not correct. F first, F inverse circle G inverse. Okay, so proved, hence proved. So this class is very difficult for you people, I think. because all are theorems only, no problems. Okay, important theorems, these all.